All right, physical science students. So we have here what we left off with the other day, talking about work. We've been talking about energy, and energy is having the ability to cause a change in one's surroundings, which again, very vague, very general definition. Now I'm saying that work is this thing that we can do. Working is being able to transfer energy through motion to objects and systems. And we said that there's two things you have to do to be able to transfer energy. You have to exert a force on an object, and you have to do that through a certain change of position. The object or whatever you're doing, there has to be a change in position in the direction of the force that you apply. So you're going to apply a force, and there has to be a change in position from that force that is exerted. Okay? Now, we have been using energy pie charts to kind of discuss how energy has changed from, wait a minute, did I? Oh, yes. How energy changes storage mechanisms from like elastic to gravitational and then to kinetic. And so the mechanical energy we've been talking about can exist in multiple different ways. And so we've been talking about how energy can change in how it's stored. Well, now apparently we can actually transfer energy to objects by pushing or pulling on them and moving them in the process. So again, if I take this Super Ball here and I just hold it up, am I doing work by holding up the ball? No. I am exerting a force, but am I moving it? Well, I moved it to get to this point, so I did some work to get it to here. There's some working was involved. I exerted a force. I moved it through a distance. It actually has some elevation now. And so, but that's done. I'm not still working, although I am exerting a force still. I'm not continuing to transfer energy to the object. I did a little. I transferred some energy, and then I quit, even though I'm still exerting a force holding it up. I'm not still transferring energy because the motion is done. Now, this brings up this thing that's called the work energy theorem. All right, work energy theorem, which can be kind of complicated and cumbersome, but I don't know. I'm just going to make it simple. Okay, here's the work energy theorem. It says that if you do work, if work is done, then the amount of work you did equals how much energy change occurred. That's that. When you do work, it makes a change in how much energy there is. Doing work on something changes how much energy that something has. Now, that leads us to something called an energy bar chart. And it's going to look kind of complicated, but it really is. I call it a LOL chart. A LOL chart. L-O-L. LOL. I lolled a lot about the fact that I came up with that name for that chart. So anyway, we're moving away from pie chart, energy pie charts, and moving now to a energy bar chart, or energy flow diagram, it's sometimes called. So here's how this works. Okay, we're getting a little more quantitative now. See, the pie was good, but the pie could only do so much. And carving out little slivers of pie that represent this or that or the other, it gets a little. We just can't be as quantitative as we'd like. All right. So the way this chart works, and hopefully I'm going to do a couple examples together with you, and then you'll see that. And then there's actually going to be an assignment that you'll work on that has a bunch of energy bar charts with a bunch of different scenarios. Now, if you'll notice, we have initial and a final. Now, in the energy pie charts, we had like an A, B, and a C. We even had some scenarios where there were 5 pies that we had to divvy up. Well, now all we have is an initial and a final. We have an initial, we have a final. So, initial, we look at the beginning and we say, okay, is there kinetic at the beginning? If so, how much? Is there gravitational at the beginning? If so, how much? Is there elastic energy at the beginning? Okay, how much? And we have these little levels here. It's a bar, and depending on how tall we make the bar, like this would be 1 block worth, this would be 2 blocks worth, this could be 3 blocks worth of a bar. So we're making bars that are like so many blocks high. So we're kind of quantitatively deciding how much energy there is based on how many blocks that bar is made up of. You could even do half blocks if you'd like. But initially, we're only going to be dealing with the mechanical energy. We have, again, the kinetic, we have the gravitational, and we have the elastic. Now, we'll get to this energy flow thing here in a second. And then final, so the final snapshot, the after, so we have a before and an after, an initial and a final. We have kinetic possibility, we have a gravitational possibility, we have an elastic possibility, and then we have this internal energy thing. That's kind of what we were calling dissipated energy before. And instead of calling it dissipated, now they changed names and we call it internal. Now remember, like in the scenario where the super ball was bouncing and the super ball would only bounce would only bounce so high and it got lower and lower each time. The internal energy we're talking about is the jostling of the particles in the system from the floor to the ball itself. The particles in the floor and in the ball get jostled around every time this thing makes impact with the ground, and the ball gets compressed and it springs back to its normal shape. Every time that happens, the particles in here get jostled about. Okay? That's thermal energy. When the particles themselves are getting jostled around more than they were before, that is thermal. Now, the problem is it's so little, we can't even measure how much it is. And so we just call it internal energy. It's in there, but it's so small we can't even measure it. But ultimately, it is thermal energy. It is the jostling and moving of the particles, which we had already defined earlier in the year as thermal. So that could be involved as well. Now, again, this little circle thing in the middle, we'll get to that in a second. So my first example that I'd like to take a look at, and I got to get me out of the way here. I'll put me down here. The first example here is a little ball on like a little ramp here. We've got a little, it looks like maybe a quarter pipe skate ramp. So there's a ball at the top of this little ramp. And then the after is the ball at the bottom of the ramp, and apparently it's got some motion. So, initial, the before shot. What do we have here? Well, I hope you see that there's some elevation, right? There's some elevation above the ground. Do we have anything that's been compressed or stretched or twisted or wound? No, I'd say no. Is the ball moving in the before picture? No. So I'd say all we have is gravitational. Now the question is, how much gravitational do we have? I don't know, make it up. Is there only 1 block? Are there 2 blocks? Are there 3 blocks? I don't know. Because that's the only thing we have, I'll probably just say there's 4 blocks. We maxed it out. I mean, it's maxed out, 4 blocks. Or I could say there's 3. Maybe there's 3. Okay, I'll say there's 3. I said I was going to max it out, and then I changed my mind. Uh-oh. Oh, no. I got to click in the darn thing here. Jeez. Now, am I even owned? What is, oh, no. Is this thing, oh, it's frozen. No wonder. My screen's frozen. Sheesh. So, I need to get my pen. I need to get this to, okay, it is orange. So, let's say 3 blocks worth. So I'm just drawing a bar. I'm drawing a bar on my energy bar chart, on my LOL chart, that shows, hey, I have gravitational at the beginning here. And I have 3 bars worth, 3 blocks worth, I should say, before. Now, the after picture. It's at the bottom of the ramp. Do I have any height? No, it's at the bottom now. There's no height. Is it moving? Yeah, there's kinetic energy now. It's moving. Has there been I have the hiccups. I don't know if you can tell. I need some water. Is there any elastic? Like, did the ball get compressed or stretched or whatever? I'd say no. Probably it just rolled down a ramp. So I don't think there's any elastic. And honestly, I don't see any evidence that there's some kind of internal energy. I mean, I'm sure there probably is. I mean, anytime a ball is rolling down something or whatever, I mean, there is some jostling of the particles. So I suppose we should put some internal energy in there. But here's the thing. I usually don't unless there is some clear evidence that we are missing some energy. That some mechanical energy in the system is no longer there. Unless that's clear and there's evidence of that, I usually don't bother putting E internal in there. Because I don't have to. I'm making it up myself. So I think that all of the gravitational that it started with has become kinetic with the rolling down of the ball. So I'm going to say that my EK, I have 3 blocks worth of EK after. Oh boy, that was weird. So I have 3 blocks worth of EK after. I had 3 blocks worth of gravitational. Now I have 3 blocks worth of kinetic after. And here's the deal with the energy. We know that energy cannot be created or destroyed. So that means with our energy bar chart, everything we have initial, we have to have final. If you got 3 blocks here, you better have 3 blocks here. That's kind of like our pie not changing size in the pie charts. Whatever we had before, we have to still have after. And if it's not there, we have to have some reasonable explanation. And again, that's where energy internal comes from. So there has to be a reasonable explanation if we're missing some of our mechanical energy that we started with. So that's just a very simple, basic example of what a energy bar chart scenario could look like. Well, here's another one. Let's move me over here. So now, and let me get rid of this. Oh no, let me get rid of that bar. Let me get rid of this bar. We'll start over. So now I have, I probably locked all those in, didn't I? Yes, I did. I can't even move it. So we have a person on top of, I don't know what this is. Maybe it's a wall. Maybe it's a edge of a building or something, a roof. So the person has a ball. Person throws the ball up into the air. And so the question now is, what kind of energy do we have here? What kind of energy do we have initial and final? So before and after. So in the before picture, what does the ball have? I hope you're thinking gravitational, because it's quite elevated here above this bottom, whatever the ground is here. So it's way up here. Person could just drop it, and then that gravitational could become kinetic, right? But the person is holding the ball right there, elevated above the ground. Now, is that a lot of energy? I don't know. And here's the deal. And here's, we probably should not go a full 4 blocks of gravitational here, because what's going to happen? In the after picture, it's even higher. So we probably don't want to max out gravitational with 4 blocks, because I think we're going to have even more. So don't max it out, if that makes any sense. So I'm going to say maybe 2 or 3, 2 blocks of gravitational. And again, because I'm thinking ahead to what we're going to have in the after the fact. and it goes even higher. So I don't want to max out gravitational right off the bat. So we'll just say there's 2 blocks of gravitational at the beginning. Now, if we look at it in the after picture, does it have height? Yes, it has height. In fact, it has more height than it had at the beginning. How much more? Well, I don't know. It was down here in this area, and now it's up here. So how much more does it have? I don't know. Is it maybe a block's worth? I guess it could be. It has gained a block's worth of additional gravitational energy in the final. Okay, so a block's worth. So now, instead of only 2 bars or 2 blocks of gravitational, now it has 3. It has even more gravitational than it had before. Okay. Is it moving in the final picture? Yes, there's lines of motion here. The person threw it. So it's moving. Well, how much kinetic do you think it has? I don't know. I mean, I guess I'd have to make that up too. How much kinetic do I think the person gave it? I don't know. A block or 2? Just a guess. A block or 2, maybe? Maybe 2 blocks? So, 2 blocks of kinetic. Again, we're making this up, folks. We're making it up, okay? Now, here's the problem. What did I say a second ago about the initial and the final? Whatever energy you have at the beginning, you have to have at the end. We only have 2 blocks worth of energy in the beginning of this thing. The ball was right here. It was elevated above the ground. Now, all of a sudden, there's 1, 2, 3, 4. Now there's 5 blocks of energy, final. The question is, how did it gain 3 blocks of energy? It gained 3 blocks of energy. Where did that come from? Well, let's scroll up here. What does it say? Work is the transfer of energy through motion. To transfer energy, you must exert a force on the object. Move it in the direction of the force I apply. Did the person exert a force on the object? Yeah, that's that's throwing it. So, oh my gosh. So the person took the ball and threw it. They exerted a force. They transferred energy through motion. They did some work. Well, that's what this part of the diagram is for. So here's how we explain this. We say, hey, there was something that was done to the ball in the before to the after here. Something got done. Some working happened. How much? Well, it appears, and this is how I would do this. Notice I'm drawing 3 blocks worth. I'm drawing 3 blocks worth of energy going into the system. That's like an arrow point there. That's what I'm doing, an arrow point. And what's happening here is work has been done. What did we say about work? Well, up here it says the amount of work you've done is equal to how much change in energy the system has. So, how much more energy is there at the end than we had at the beginning? 3 blocks worth, which means the person had to have done 3 blocks worth of energy afterward. The person did 3 blocks worth of energy, or did 3 blocks worth of working on the ball and gave it some energy, transferred some energy to it by doing work on it. Hopefully that makes some sense. So, yeah, it's getting a little more complicated, but here's what we need to know, okay? Mark this in your brain somewhere. Everything we have at the beginning plus what goes in has to equal everything we have at the end. Okay? Everything we have at the beginning plus what goes in has to equal everything we have at the end plus what goes out, because you could transfer energy not just to something, you could transfer energy away from something. Transferring energy can go either way. You can transfer energy to something, or you can transfer energy away from something by working. So this energy flow diagram here, it can show energy flowing into or out of a scenario. In this case, the person was doing some work by exerting a force on the ball, making it move faster and giving it some more elevation than it had before. So I hope that makes sense. This is kind of how the energy flow diagram or the energy bar chart or the law diagram works. I hope I've explained enough to where you can actually start to work on this. It is posted on Classroom, so I would like you to take a look at that and try to do those energy bar charts. So until next time, I will see you later.